Today, I'm going to take it relatively easy. We're going to talk about protocol security. So far, what we have seen is how packets are transferred in a network, how you can mess with the delivery system, how you can interfere in communication, wired, wireless. Now we go one step up. So we're going to talk about protocol security analysis. So the basic idea is that you take an application protocol, can be anything, okay? And you have to sort of represent the protocol and perform protocol runs, which are interactions between client, server, if they have two parts of the protocol, could be more. And in a way, you have some model of the state of the people participating. And you want to understand if this protocol can be violated. So we saw a fantastic example last time on Wednesday when we saw how the four-way handshake used by WPA2 has been recently attacked, not by breaking the actual security of the protocol, but by creating a sort of a special condition in which the initialization vectors are reinitialized. And so that was an interesting thing because I was thinking after class, that's a classic example. There are a lot of people, security experts, that look at something and say, yeah, go. And then there is somebody who's like, what if we look at this way instead? And suddenly, you have a vulnerability. Those are really the moments where you think that security can be taught, but also it has to be taught by example. I think that the only way you really learn about security is by looking at a ton of vulnerabilities, exploiting them, understanding what's wrong. And after a while, you start seeing the patterns. So what I'm trying here to do is by exposing you to various problems in this protocol, hopefully show you some patterns so that you're able to identify new patterns or instances of these patterns when you are in front of a protocol. So when you analyze a protocol, usually you have to think about the assumptions that have been made by the protocol designers. And remember at the beginning of the class, we talked about this oblique thinking or this different way to look at things and say, what was in the mind of the protocol designer at that point? And where is it putting his or her trust at that point? And can I violate that particular assumption? And we will see. And of course, now you know that you can sniff, spoof, and hijack a bunch of stuff. So whenever you look at protocol, now you know what are the building blocks that you have at your disposal for an attack. You can say, oh, look, there is this DNS thing. Oh, first of all, I can sniff the network and get the thing. Oh, I can do ARP spoofing, actually be a man in the middle in a UDP interaction that is a DNS request, and so forth. So now you have really the skill set for doing things like that. And then, of course, when you exploit something is because you stretch the limit, you violate the assumption, something that will bring the system to an insecure state. And of course, you can look at design, but you can also look at implementations. For example, we will see that there are, we will see the hard lead bug. It's not a protocol problem. It's somebody implemented the protocol in a careless way or with a bug, call it whatever they want, and therefore you can find problems. In other situations, you can have things that are misconfigured. And we talked about downgrading attacks, which are a possibility, but you can have some configuration of the protocol that because of a specific configuration of the client and a specific configuration of the server do not work well together. The implementation of that particular round of a protocol is actually insecure. And application protocols are, there are so many. There are some that are more important, like HTTP. We use it, all the time. We have a whole thing about, HTTP security and web security. So we're not going to talk about it right now. But you can find tons of protocols. So it's always a great exercise if you're interested. Whenever you find yourself with the new, latest, greatest application, now you know how to sniff a protocol, create a proxy, do something to look into what it's exchange, for example, between an app on your phone and the backend server, try to reverse engineer what's the value of the things. How can you interfere with that? It's, as a research topic, is very fun to do. It's a very rewarding activity. We're going to talk about an old protocol, the file transfer protocol. You can tell it's old because the RFC is in the 3-digit 172, and this is a protocol that is I like because it's first of all it is sort of already still there. There are devices that they update their firmware using FTP. The basic idea is the client connects to port 21. That's where the server lives, on port 21. And usually their username and password that are sent on the clear in the network. That's why FTP is not very prominent anymore. People use SFTP, the secure version of FTP, or use secure copy or other things. But this is still interesting. Mostly because I love the fact that the data and the control channels are on two different connections. So when you connect to a server to port 21, the actual connection afterwards is from the server to the client to port 20. It's kind of crazy, but at that time on the internet it worked very well. It used to be a very popular protocol in many ways, and the server and the client determine their local ports using these port commands. These port commands that say, hey, please connect from your port 20 to a port on the client. So did I say to the client? I mean, it's from port 20 to the server to a port specified by the client, and then the data is transferred. So to clear all confusion, this is the standard way. So there is a client with IP address A, B, C, D. There is a server with MNOP as an IP address. The client connects to the server on port 21, sends a username, and asks the server asks for a password. You send the correct password. Hopefully, if it's incorrect, you get rejected. Otherwise, say OK. And at a certain point, the client tells the server, hey, port A, B, C, D, E, F. That means whenever you have to send me data, send it to IP A, B, C, D, and to port E, higher bytes. So you have to multiply by 256 plus F. Those are the 2 bytes in network byte order that specify the port to which send the stuff. And the server say, OK, got your port. We're good. And this guy say, OK, give me this file name. At this point, you see, it's from port 20 to the port E256 plus F. So the server is opening a port to an IP address and a port specified by the client. Okay? At this point, all of you must be, yeah, there is an obvious problem here, right? What would be an obvious problem? You could get a different port on the client, yes. And then why would that be a problem?
Unexpected traffic, you could somehow hijack something.
Perfect. For example, there could be a server, and you can have this server, connect to a port that, for example, you can't control, and you want to send some traffic. Somebody has something else to add? Yes? If you send stuff, the port doesn't exist, this will just be resetted, no problem. Yes?
Does the server care about the ABCD that you specified?
Exactly. The server cares about this and will actually connect to whatever IP address you specify, right? And the funny thing is that this is actually by design, as we would say. It's not actually a bug, quote unquote. The other problem that you saw in that moment, in this diagram, the problem that you see here is that you have a server to client connection. This, at the beginning of the internet, not a problem. Then security became a concern, right? Now, if I have a firewall here, okay, it's very easy for me to say, hey, allow connections out, but do not allow connections in. Usually all the protocol that we know fundamentally have a client connecting to a server. This is a server connecting to a client. So a long time ago, people say, well, how do I allow FTP connection? Oh, I'm going to open from port 20 to anything to allow these data connections in. And guess what? The bad guys were just creating connection from port 20 to anything, even though there was no interaction with them. And then there were stateful firewall that would say, oh, I will monitor what's happening here, and only when I see this type of command, I will open the necessary port to allow that incoming connection into my network. But the firewall people really didn't like that. And so the SU introduced the passive mode. In passive mode, fundamentally, is the client that say, okay, I would like to operate in passive mode. So when you specify this connection, say, hey, I want to connect to this address of yours, then you open the connection to the port, and you ask to retrieve the file name using the command connection on port 21, and the data is sent. So the important thing is that the connection here is open from the client to the server. So at that point, from that point on, fundamentally, everybody uses passive mode, because in that particular configuration, everything will go always from a client to a server in terms of opening connection. And FTP, has a bunch of weaknesses. Username and password are in the clear, bad. We know that. All the session traffic is unprotected, so you can sniff, you can hijack, and you can do bounce attacks, and we will see what those are. And of course, there is also anonymous FTP. That is something that is, of course, not as popular in the age of what we have today in terms of file sharing. By the time, it was a way in which people would distribute software. They would say, oh, this is anonymous FTP. You can log in and access software, for example, without having to provide a password. It's a way just to share information before Git and other, software distribution site. And this caused a whole bunch of problems, because you would open fundamentally an access to your machine to anybody. That means that, okay, if the implementation is perfect, you can only do those small commands on a machine, but and sometimes that had upload directories where you could store files. But a classic example was, to upload a file to an anonymous FTP website and then retrieve that same site using the web, because the web and the FTP, the anonymous FTP, were sharing some directory. So you would upload anonymously a PHP file, then you would request it through the web server, and suddenly your PHP code gets executed. That would be not good. You have somebody able to upload executable code to your server. Interesting is also the FTP bounce attack. And it is in the RFC, let's say, if you look at the RFC of the FTP protocol, let's say, it should be noted that the data port need not be in the same host that initiates the FTP commands via the control connection to port 21, okay? But the user must ensure that there is somebody listening on that port. So in the RFC, they said, you don't have to send it to the same host. You can send it somewhere else. And of course, this means that you can send stuff to a third host, and this is a classic design that makes sense in a trusted network where everybody's like, oh, we're all friends. We're trying to make this thing work. We want to transfer files. We want to make it easy. Suppose that I have a server somewhere, in my lab, and I'm logging in from this, stupid terminal, and I want to get this file. I want to store it on the lab. I would just, say, hey, send the file there. Super flexible, right? But of course, this can be abused because you can just specify the bounce attack a different IP address, and so you had a connection from port 20 to a port that you specify on a different machine. For example, you can specify port 80, and suddenly you're doing posts on a website from this machine. Okay? So fundamentally, if you are able to upload data here, you can send any traffic from this machine to this other machine. And of course, this can be used to do TCP Port Scan. For example, you can actually bounce off of the server to create, to scan an internal network. And many, many years ago, I found myself exactly in that situation in a real world. I was testing a bank, and they had this FTP server. And from the outside, we couldn't see much services, but then we bounced the scan over of FTP server. So we say, hey, port, 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 port. And from the error message, we could tell which port were open, and we had way more accessibility than we would have from the outside. And so we would know what services were running, and we could even attack them because we could upload files to that server. Also, if there is a relationship between the actual FTP server and other elements of the infrastructure next to the FTP server, you can upload a file and, for example, send traffic that could have, adverse effect on the security of the system. For example, in the good old times, there was remote shell would allow you to execute commands only if you come from a certain specific IP address. So in this situation, remote shell would function at port 514. If this machine has a server for remote shell and trusts this other server, because, for example, they are in the same network, I could upload a file up here in this server that has this schema, a null byte, the string root, null byte, root, a null byte, and something that would add a particular account to the etc password file of a Unix operating system, which, in a long time ago, would allow you fundamentally to log in as root with whatever password you chose here. You would upload the file and then ask to retrieve the file, specifying a port that was 514, so 256 multiplied 2 would be 512, plus 2, 514, and the file would be sent here and interpreted like this, interpreted by the server here as a request to execute this command, which will add an account, and then you could log in without any problems. Okay? So, well, instead, of course, the bounce scan works in a similar way. You start specifying a port on the host that you want to scan, for example, port 6000, and you ask for a list. If you get something that says successful file transfer, you know that the port was open. If you get connection refused, you know that the port is closed. And so you can sort of bounce off your port scan using the FTP server. So this is just, of course, an example of a now obsolete file protocol, file transfer protocol. Nowadays, as I said, use SFTP. I think that there is no reason for using the FTP protocol. However, you will be surprised that you can nowadays analyze, for example, a piece of medical equipment, and long and behold, you have an FTP server running on it. And at that point, this should ring all the alarms that you have at your disposal, because similarly, if you see a telnet account, because of course of all these different issues. But let's talk about something more interesting and something that we use every day, the domain name system. So this is a simple system that, as you know very well, it maps domain names to IP addresses and allows you to, find out who lives at a specific domain. This is because we're very good at remembering names like longboard.csucsb.edu, but we're very bad at remembering, IP addresses like 128.1.1.48.69, unless you are, one of those people that prefer remembering numbers. I'm not one of those, so I remember this is one of the machines in my lab, and so in order to allow this, we the internet has created this hierarchical system called the DNS, where each domain is managed by a specific server. It's called the authoritative server for that particular subdomain. And the clients access this using something called the resolver library. So in C code, you will see calls like get host by name, get host by address, and the library takes care of making the right invocation to the DNS and return the information that you have. DNS uses mostly the UDP protocol, but can also use TCP either if the answer is very big, and so you need to transfer more data than can fit a UDP packet, or when doing zone transfers. And we see zone transfer are a way for multiple DNS to keep their information replicated correctly so they can both serve the same set of requests in a consistent fashion. But UDP is still what's used. And it's used because UDP has less overhead, and so that helps with the traffic. So this is a look at the domain hierarchy. You can see that there is the root up there. So funny note, every fully qualified domain names like www.google.com should end up with a dot, but is actually never used. But you can use that to impress people at a party. If you want to map the reverse, as we will see, the IP addresses are structured in sort of like a fake domain that starts with ARPA, in, other, and then there are the octets, and this is where we would store the name associated with this particular IP address to create the connection from IP address to name. But here you have, your .com domain, and then you have, Apple, Microsoft, Intel, and www. You have gov domains, called second-level domains, and then you have, UCSB. You can have a department, and you have, various elements. You're very familiar with this. Yes.
What about the domains in other countries, like RU or?
They're all under the same umbrella. So you have, as we will see, there a lot of different domain. I'll get to that.
Okay.
I'll cover that. So, so I explained that in order to map IP to domains, there are this dedicated branch called, ARPA in other. Also note that a name can have multiple IP addresses. For example, if you want to have redundancy, a way is to have one DNS name with multiple IPs, so you can serve that IP whenever you need. An example that should be familiar to you, if you look for cecil.cs ucsb.edu, you get sent to different places, okay? Depending on the availability of the system. And also an IP address can have multiple names. This is classic when you have multi-hosting. So you have, a web hosting company as one IP address and 300 websites running on that particular host. This, for example, makes it really hard to use IP addresses as a way to blacklist things, because you say, oh, that's a terrible website. Let's blacklist the IP address. Somebody say, hey, I cannot go to my cat site anymore. Well, this IP address is bad. Well, no, you have this horrible website selling, fake, pharmaceutical, but on the same IP address, you have a perfectly legit site about cats that everybody loves. So you have to be very careful about that. The name servers are the ones responsible for answering questions. There are root servers that are associated with the top of the hierarchy. There are 13 of them. They're very important servers because when nobody knows where to start, they go to these 13 servers, and therefore they're actually a pretty severe target for denial of service attack. If you could take down all the top 13 servers, you would be, after the caches that are around expire, you will be able to considerably affect the ability of people to resolve names. And there have been attempts at denial of service against the servers, but usually they are so well guarded, load balance on super fat pipes that actually DOSing them all 13 of them is incredibly hard and has never been achieved effectively. In normal servers, we have primary servers. Yes?
So what would happen if somebody managed to, I don't know, like blow all of them up or something?
Say it again?
What would happen if somebody managed to destroy all of them? Like, you know,
Oh yeah, put with a bomb. Yeah, that would be pretty bad. But I think tracking all the machines, I think you can do worse. I mean, if you have to put all the amount of effort, but yes, if you destroy physically all 13 of them, it would take a little bit to come up with other machines that would run on the same IP address, and soon the disruption would be noticeable but not catastrophic.
So there's backups?
Yeah, of course, these are IP addresses. There is a configuration file with IP addresses. There are many machines that are load balanced behind those IP addresses, not just one desktop that is serving the internet. So taking them all out, I'm sure that that's a Mr. Robot kind of plot, possible yet unlikely. But yeah, I mean, you could do some damage. Also, you can have secondary servers, which are sort of backup that allow for load balancing or to serve the same data. And these are the ones that synchronize with each other using zone transfer. Then you have caching only. There could be servers that just resolve the stuff and then remember it. They're not doing anything else but resolving recursively a query, remembering what was the association, so that for a while they will provide the same data. Forwarding, that just act fundamentally as a proxy, and recursive server that will just recursively serve all the information that you want. And interesting, there are some recursive server that could be open. That means they do this for anybody. Okay, so that means that somebody across the internet could ask them, hey, can you resolve this name? And they will resolve the name, which can have problems because if you now know UDP packets can be spoofed, so I can generate very, very big queries and use these servers to reflect traffic against somebody and cause a denial of service attack. And fundamentally, if a server of this cannot solve a query, it's sent to up in the hierarchy to find out how to resolve it. This is more of a technical thing. Whenever you're looking what is your current server on a Linux system, when you find yourself on the cloud and you're concerned if something is not working, is the file atcresolve.conf that usually has the information about which name servers you're actually using. And tools that are useful for querying this thing are a tool called host, that's the actual name of the tool, or something like dig. So the recursive queries are two different type of queries. A recursive query, you fundamentally say, hey, server, I need this information. Go find it. An iterative query is like, hey, server, what should I do next? You get an answer, and you operate on the basis. And note that if you receive a reference to the next step that is necessary for resolving the name, the reference around the server contains both the name of the name server and its IP address. It's called glue data. And so you say, hey, this is where you should go next. By the way, this is the information about that particular host, so that you don't have to query for that information, who could generate another query. And this is kind of important. We will see later. As I said, the root domain is an implicit domain. There used to be few TLDs, like the various country domains. The top level domains were the country, were com, biz, org, net, and so forth. But recently, everything has been expanded massively, and now you have .horse, .me, .eu. No, EU was there before, I think. But a lot of super weird domain name. As I said, the root name servers are super protected. There were a few incidents in October 2002. There was a big DOS. Another one they had in 2007, and is 2012. There was a threat, I think by Anonymous, but I think that was never actually taken out. If you look at the DNS query from sort of a TCP down perspective, it looks like this. You can see it's a UDP packet. It goes to port 53. 53 is the port where DNS lives. And you can see that in this case, you're asking for the address, so it's called an A request, for morgan.ec, ucsb.edu, and you have the reply that says, hey, that's the address. And if you want to do the opposite and say, hey, I want to know what names are associated with that address, you do a pointer query, okay, PTR, for this address. You can see that it's in reverse order and stop with in other ARPA. And you get a pointer request that tells you that that's the host name associated with it. Okay? If we look at it from a graphic perspective, if there is nothing cached, this person would say, hey, how do I resolve www.bank.com? At this point, this server, if it has nothing in the cache, will say .com. Let's start with this. I have no idea where .com is. And of course, it will go to a root server and say, where is the server responsible for .com? And you get an IP address. And then it will go say, okay, who is bank.com? And you will get another IP address for another domain server. And then we'll ask this domain server, okay, I'm interested in www.bank.com. You will get an answer, as this is the answer that you will send back to your client. Okay? Yes?
Which one actually supports these top-level domain servers?
Good question. A number of different, I just super recently went through the list. There are different organizations. They do that, I think, to support the internet. I can look during the thing. There is, you can go to, if you look for top-level root server, I think one is at Stanford, if I remember correctly. Others are in other place, University of Maryland, things like that. Other questions? Yes.
Does that mean that the .com server has to have every single .com website?
Correct. This is the .com server, this guy. Okay? It will tell you, he knows about .com, Verizon.com, foo.com, bar.com. It knows where DNS servers is.
Okay.
So if I am responsible for the .com domain, it's a pretty big job, right? But I know where is the server for Verizon, the Verizon domain. Then inside Verizon, you go to the Verizon thing, to ask for a specific host.
But there's not a hierarchy within the .com?
No. I mean, there is a lot of load balancing. It's not, again, when I say a server at this level, is not a desktop running on somebody's desk. It is a huge data center. I think, .com, I always forget. I remember it's not, I think it's run by VeriSign or something like that. But, they have a huge infrastructure to answer to that, important query. And also you have to understand that most of the time, this is cached. Because it's very infrequent that you have domains, you have a long tail of domains, but for those there is not a lot of traffic. So the data in the DNS is structured in called resource records. So you can have the type of record. For example, the Amex record is what tells you, hey, I want to send an email to vinya@cs.ucsb.edu. So how do you find out who to contact? Well, you go to the DNS and say, cs.ucsb.edu, who's your mail exchange, Amex? The DNS will say, oh, you have to go to stamps or letters.cs.ucsb.edu, and then you go there, you contact port 25, and using SMTP, you send an email. Of course, you can have a record and pointer records, as we have seen before. There is a class of resource, for IP addresses is IAM. Time to leave. So you also want to specify how long you should or want to keep this in your cache. Then it's, of course, up to you to decide if that's the case or not. Length of the data, contents of the data. These are all records type. Start of authority, named server, if you want to specify, hey, this particular record referred to another named server for a domain. We saw the A pointer. CNAME, canonical name. So if a host has many names, you want to provide one that is his real name. Hinfo, for example, this is something that provide host information about the host. This was used and abused quite a bit at the beginning, before people realized that giving to everybody, what is your operating system version and patch was not a good idea. And also WKS, the well-known services running on a host. You can see that you could use this information in addition to a port scan to gather information about a specific network. Other example are pointer domains that are used to map IP addresses. We talk about MX, mailboxes, mail rename. They're all these different information. And you can see that the DNS fundamentally is used as information exchange system. It's just a queryable hierarchical infrastructure that is used to store all sorts of information. Host information, mail information, IP address and domain, and so forth. So there are several weaknesses. First of all, it's based on UDP, so it's vulnerable to spoofing and hijacking. You can race against a DNS server, or you can spoof a particular server. Implementation that trusts too much the information returned by a server could be vulnerable to a series of cache poisoning attacks. We have seen throughout history a bunch of those. Once again, now people are, as we will see, there is a series of checks that have been done and then being broken, then been done, and then improved and broken. But it's always, you always have to understand that here the assumption is that an application, when an application tries to resolve a name, has a lot of trust in the information that comes back from the server. So this local server say, I have to go to www.google.com. When I get the IP back, I trust that stuff. So whenever that information is manipulated, the amount of things that you can do for mischief is almost, limitless. Suppose that you go to facebook.com and I send you a different IP address. You connect there. I have a web server that replicates perfectly facebook.com. You put your credentials because you don't notice that it's not HTTPS. It's just HTTP, but statistically people will not notice. They give you username and password. So it's a great, spoofing DNS traffic is a great way to create phishing sites. So these are all things that you have to keep in mind. And as I said, long replies can be used in the denial of service attack. If you have specific repeater and you can ask that person for a host whose answer is very large because, for example, has many records associated with a particular query, I can spoof the source address of that message, send it to the DNS server. The DNS server will reply to the IP address of the source and create an amplification of the traffic. And we'll see some example. And of course, I forgot the first part. I told you about the hosting for records. I remember one of the ways you could get an enormous amount of information about a network is just connect it to some DNS server and say, hey, why don't we do a zone transfer? And some servers that were misconfigured, because you shouldn't do a zone transfer with whoever you want, would just give you all the data they have. Okay? So in one single request, you would get fundamental all the IP addresses of all the services, sometimes even the host information about CPU and configuration. And for example, I remember when I was a grad student, my department in Italy would do that. And we would have a great time because we would just connect to that, say, hey, give me a zone transfer. We'd find out printers, where they are, machines in the offices of people. And in the HInfo was so much information. It was it was fantastic. With all sorts of jokes were possible. And so I talked about this, and you can do, you can obtain a large amount of information using zone transfer. But the real attack that is interesting and often used is DNS spoofing. So the basic idea is simple. You imagine the bad guy starts a connection to a server that has this IP address, and this is a TCP connection. And sometimes there are trust relationships that are not based to IP address, but to username. So you say, allow connection to anybody who comes from parker.jazz.edu. So mingus.jazz.edu allows access to anybody who comes from this domain name, all right? So domain name are used, for example, in NFS to allow connection from a certain domain. So the IP address, the TCP connection happens, and when this server sees that IP address, asks, okay, who has this the name for this IP address? And the request, will actually go through the infrastructure, and it will end in the server that is authoritative for that IP address. If that server is under the control of the bad guy can answer anything. Can say, oh yeah, of course, I am parker.jazz.edu, even though you're not. Okay? And this guy's like, okay, you're exactly my buddy here next to me, so please come in and do whatever you want. Okay? So people got pretty soon realized that this was not a good idea, and so they introduced a concept called the double reverse lookup. And the basic idea is like the IP address comes in, I say, hey, what is the name for that? Oh, it's parker.jazz.edu. Okay, what is the IP addresses associated with parker.jazz.edu? And then you compare the results. Because if you think about it, in that case, things happen differently. So if I do a double reverse lookup, after I get the answer, hey, this IP address 115.12.22.77 is associated with parker.jazz.edu, what do I do next? I say, hey, what is the IP address to parker.jazz.edu? And who is the name server responsible for that mapping? Not the evil one, but monk.jazz.edu. And so this Mingus will ask Monk, well, who's Parker? And this guy, who's not under the control of the bad guy, would answer 192.112.15.1. It will compare that value to this and say, these two are not the same. Somebody is messing with my DNS infrastructure. So is that clear? Right. Double reverse lookup. So, yes?
What the attacker can use this IP address?
Can use the what?
Can use this IP address?
Yeah, can use the IP address, this IP address, right? Can spoof this? Not in a TCP connection.
Oh,
On UDP, yes. He's trying, the ultimate goal, this connection request, I should write TCP connection request from there. So the basic idea, the guy is using a TCP connection, and here the authentication is not based on the IP, but on the name. So they say, well, who's this IP address? Oh, I'm the good guy. And the guy say, hey, local, who's the good guy? And you get a different IP address, and you know that this is a problem. Yes?
Why did it go to the first lookup there, but go to the second lookup?
Wait, you have to repeat the question from the beginning slower.
So first time when he asked for the address for one page,
Yeah. There will be a pointer query, right? In other ARPA 7722.12.115.
So the IP to the address is located there, but the address to IP is located there.
You got it. Perfect. Yes?
Does the DHCP server have any way of authenticating who it gives an address to, so that I can't pretend to have someone else's IP?
Well, the DHCP server operates within a network, right? So the DHCP server, first of all, it's in most situations you can race against the DHCP server, so you can always do a DHCP server hijacking attack. The DHCP server also tells you what DNS server to use. Is that what you mean?
I think so, yeah.
So I can, instead of hijacking the DHCP server, I hijack the DHCP server, I give an IP address, but in addition to that, I'll give you as a DNS server an IP address under my control. That would be different from, for example, doing an spoofing attack and pretending to become the DNS server. But all these attacks, DHCP hijacking, can only happen within this local network. Okay, you cannot do a DHCP spoofing attack from remote. This is something that this attack could be on the other side of the planet. Okay, I have my server under my control. I do the connection, and when the requests come back, I reply with something that is fake. Okay.
So what prevents somebody from saying, no, I'm 168.7.7.4?
Well, because you can on the different network.
Yeah.
You could of course do it, right? You can always claim that you have certain things. But first of all, your stuff will be routed to the wrong place because you inject a packet. Okay, you can inject a packet pretending to be 168.774, but the reply packet, okay, will go to that host. It will not come back to you. So if you want to pretend to be this IP address in a TCP connection, as you remember from the TCP spoofing attack, you have to automatically learn or guess what the initial sequence number chosen by the server is. Because you're going to, for example, if you want to connect to this host, you're going to pretend to be, Mingus with this host, but Mingus is going to reply to this host. So you won't see the CNAC packet, and you will not be able to do a TCP connection. You can always send a UDP diagram however you want, provided that nowadays there is a lot of egress filtering. So you could have actually a provider here that say, well, you're sending a packet that is, a UDP packet, for example, that appears to come from, monk.js.edu, the IP address, and say you cannot go out here because, you're not that host is not supposed to be behind here. Okay? Yes.
I don't know if I followed correctly how the double reverse thing works, but wouldn't that be complicated by the fact that the relation between names and IP addresses is not objective? Like you just said, you can have multiple names
Yes.
for address, so that complicates things, right?
And we will see it in a second. Very good. Very good. No. Yes.
So, about the double DNS lookup.
Yes.
I don't understand why it is limited to TCP.
Okay.
I mean, even, so the UDP layer is one layer above the IP layer. So, if we consider a DNS implementation as access to kernel level, you always know the IP. You can spoof it because the routing wouldn't send you the UDP packet if the frame is spoofed.
I mean, the double reverse lookup works also for UDP packets. So if this person sends a UDP packet pretending to be this person, okay?
Yeah, okay. So I don't understand what is limited to TCP. Before you said that you are correct.
Okay, so fundamentally is the level, I would say, it's the easiness of impersonation. So suppose that I want to send a command appearing to be, so in this whole thing, the bad guy is trying to be parker.js.edu with respect to this guy. So if this is a UDP-based service, I don't have to go through this. I'm just going to send a spoofed UDP packet whose source IP address is this. It will get here. It will do all the DNS resolution. It will tell you, yeah, it's parker.js.edu.
So you could do DNS spoofing with UDP as well?
You could, oh yeah, of course, you could send from here something to say, hey, this is the UDP reply to this.
Yeah.
Of course.
Just a step.
So you cannot do it in one step. You would have to do DNS spoofing. So let's not distinguish between, let's not confuse two things. The DNS is the service here that you trick into creating the false mapping between IP and domain, and then there is the actual service that is like, for example, let's say RPC, port 111, the port mapper, whatever, some old service that use some kind of IP and domain as authentication. And we're going to take a break in a second, but bear with me, just one more minute. So if this is UDP, and I want to impersonate this host with respect to this host, I don't have to do anything. I'll just send a packet with a source address of 192, and a destination address to this. It will be routed to this. This guy might pick up the IP address and say, what's the name associated to this IP address? It will ask to this guy, who's responsible for this guy, will say, yes, that's Parker. One packet, the attack is done. If you want to open a TCP connection, things are a lot more complex, because you want this guy to believe that this IP address is associated to the name, so the CNAC packet is sent back to this guy. And so you don't have to do any TCP spoofing. You're just saying, hey, I am that guy. So you need that for TCP, because the impersonation attack has that extra step where you need the CNAC back to you. Okay? All clear? Okay, let's take a 10 minutes break. Of course, as we have discussed before, there is the possibility of DNS hijacking. In this case, you can race with the server. So the server requests a DNS resolution, and you provide a spoofed reply that appears to come from the server that was asked initially, with a different mapping between the two. In this case, you would achieve whatever you want. Or, you can do blind DNS hijacking, meaning that you connect to a server, you don't see their request, you anticipate whatever request is being sent, and you send a spoof reply from remotely, trying to interfere with the server. Of course, there is this little snug here that is the sequence number that is used in the DNS request. You have to guess that sequence number. So some servers, a long time ago, they used sequential sequence numbers, so it was pretty easy to do. You would ask that server to resolve a name, get the number, then create the connection and send a spoofed DNS reply with the following sequence, assuming that the server will use the following sequence number, right? That would allow to actually hijack a connection right there. So that means that if you can sniff the traffic, everything is great. You see the DNS request that is sent to you too, and you just send your own version of the DNS reply. But if you can do that remotely, even better. Another aspect is cache poisoning. This is especially malicious, because in a way you not only provide the wrong mapping, but that mapping will be permanent, so it will be used for subsequent requests. So again, this attack is based on the fact that sometimes there are problems in which information is cached. For example, a server could be too trustful, or could trust too much what information would come back. A classic example is, the fact that people would sort of receive not only from a certain server the information that they asked for, but sometimes they would add some glue data, some additional data that in many cases is perfectly benign. It's sort of like, hey, remember the glue data in the next step in the request? Oh, here's the answer. By the way, the next step lives at this place. And say, oh, thank you for letting me know. I don't have to do another query. But if you trust that information, suddenly you can do all sorts of you can have all sorts of problems and people can exploit you. So the problem is, especially if you cache that information, then another person that will come and ask you afterwards will find that that association from a trustworthy server. Okay, so that is the problem that can create the let's say a new entry in the trusted DNS that will foil the sort of the double reverse lookup. So in this case, you have the bad guy opens an IP address, open a TCP connection to this host, and you say, I am this IP address. So the host, like in the previous case, will ask this server, who is this IP address? And this guy will reply, hey, this IP address is Parker. By the way, there is some additional information that my IP address is also associated with Parker. Okay, the reverse mapping is added in the reply to the original query. Now, this information, you can see the bad guy answer with, okay, this IP address is connected to this domain. And by the way, I give you some additional information. This domain is also associated with this IP address. This is additional data that has not been requested, but is volunteered by the service to be quote unquote nice. If this guy received this information and said, wait a second, I've seen this and I'm going to actually memorize in my cache this additional information, when this guy performs the final check of the double reverse lookup, that value has been cached. And so when it asks, so what is the name associated with parker.jess.edu, the DNS server has cached that information and will reply, this is the IP address, I know it. And therefore, you will pass the double reverse lookup. Okay? Because that means that the cache here has been poisoned. And now it remembers something that is not correct. In a way, this is similar to what happens with ARP spoofing. You're poisoning the cache of the ARP server so they remember the wrong thing. And so when they have to route stuff, they route it to the wrong link level addresses. So how do you solve this? Well, there is a thing called the bailiwick checking, or the bailiwick check, which is if I ask you something and you give me some additional information, I'm going to remember it only if it's something relative to the domain I ask you about. So the problem with the previous scenarios that we just saw is that we asked, about an IP domain, okay, and then there was something that was returned that had nothing to do with that particular server. This server is not responsible for this mapping. This server is responsible for the mapping. So a way to prevent this from being a problem is like, hey, I just want you to give me back as additional information things that you are authoritative for, okay? So something that you are responsible. So if you give me this additional information, it's okay, because I would come to you to ask for that additional information in any case. But just don't give me additional information that you're not responsible for, okay? Of course, you can try anyway to do it by answering a query that comes from for a specific host with fake replies that have additional information for that host. So for example, you could, if somebody is asking, somebody say, oh, where is www.wellsfargo.com or bank.com? If you are able to provide a fake answer that appears to come from the authoritative version of the name server for bank.com, then you can actually add additional information for that domain that would create a binding between name in bank.com and machines under your control. So the next time they go to another of this domain, they will go to your machine and not to the one from bank.com. Of course, in order to do this, you have to guess the right sequence number. That's why sequence number are randomized, so you cannot do this little trick, okay? And of course, also, if the attacker loses the race, so you're not able to give the right answer with the right sequence number, then the correct result is cached, and you have to wait until a new request is done. So this is not an attack that is very easy to do, okay? So imagine, so this is a race where you try to add additional information to the cache. If you miss the race, which is very likely because you have to guess, the sequence number for the DNS packet that, is big and it's random, you miss it, and then for, minutes, hours, days, what the correct answer is cached, and so everything else will be ignored, right? And this worked for a long time until somebody came up with an interesting attack, which is actually based on the birthday problem. So let's try this experiment. Let's start from here. Tell me not your date in terms of year, but the day and month where you were born.
July 6th.
Anybody has the same date? If you have the same date, raise your hand. October 18. September 18. All right, collision. It works. That's why it's called the birthday attack. And it's actually very interesting. We'll see how it works. So it was found by a famous security researcher, Dan Kaminsky. And the basic idea here is that we want to poison the cache of a recursive DNS server. So we want to convince somebody to whom people go that there is a particular mapping between a specific domain name and an IP address, usually under my control. Okay? So we try to hijack so we want to do the poisoning by sending the right answer at the right time with the right sequence number. Okay? But the problem is that the sequence is random, and the source port is most of the time not randoms, and it can be easily removed because, of course, the request is from a random port to 53, and so the reply has to be from 53 to the random port. But the port is not as random, and oftentimes if something is behind a NAT, for example, it could be easy to de-randomize. So the basic idea is, hey, Paul, please. Paul could join us today. Awesome. Paul is in high school, so he's jumping a few steps to grad school. It's gonna be fine. So the attacker sent to the DNS server of a victim multiple requests for a host in the same domain of the target. So I want to poison the victim. So if that person, I want to convince the victim of a certain mapping, I ask that victim for a specific domain on the target. The target is what you want to impersonate. At the same time, the attacker sends a number of spoofed replies that appear to come from the DNS server of the target, the one that you want to impersonate. Okay? The difference is that you send a lot of spoofed replies. And the birthday attack is you want to create a collision. So you want to send a lot of requests and a lot of reply, hoping that one of the two match. So to explain the birthday attack, so what we just experienced in class is exactly a collision. There is a function that tells you, if you can find two inputs that produce the same output, as you have seen in crypto, you have a collision. So if a function has results on a large set with equal probability, there is, a certain probability that you have a collision. So for example, if, we have here, the space of birthday is 365 days, okay? We have now I don't know, if you have finding two people, to find out how many tries you have a good probability to finding two people with the same birthday is, pretty limited. So if we have 23 people in class, which is pretty much what we have here, we have a good probability that we have a birthday collision. And in fact, we had to win very soon. I think I would say I got pretty lucky. And since it happens, I probably taught 5 editions of the class, and 4 out of 5 had a collision. So I'm a lucky 50%. So it's, of course, if instead the sequence number is 64K, you don't need many attempts in order to find a possible collision between the two. So because of this property, the idea is this. There's a description there. But fundamentally, this is the victim, okay? The victim will believe what this guy is saying, okay? This is the name server of the victim. Now, as you can see, this is some spoofed information that will be sent as an attack. But first, we have to trigger, request to this. So fundamentally, the bad guy asks to this victim, hey, can you resolve this domain? This will cause multiple times a request to the authority of this server. And this will take, it doesn't exist, it doesn't exist, it doesn't exist. However, this guy will also, will say something about this random domain that doesn't exist with some additional information from this domain. For example, that the www is on a machine whose IP he controls. And these fake replies have these random names. And since now they don't have to match this, don't have to match, a single specific of this. You just have to have a bunch of the IDs in this way to match one of this in this way. You can create a birthday attack. And so one of those would match because of the birthday attack. And this server, since it will believe the additional information because it passes the bailiwick check. Here, the additional information is from the same domain that we're asking for, okay? And therefore, this additional mapping will be checked. So, to summarize, imagine this. You want to convince this server to generate a lot of requests, okay? And you want this, and you can do this in various ways, okay? So, but you want many requests, and you can make sure that they're all next domains, so nothing gets cached. At the same time, you reply as you were this guy. So it says spoofed from 7777, and you say, by the way, yeah, there is, this host is mapped to this address. You don't really care about it. It's a random host that you're just using to generate requests. The cool thing is the additional value, the glue data. Because this glue data now will be accepted and cached by this guy because it is related to the same host. And so you say, oh yeah, I will not accept anything, but since, you ask me for, the server say, I will not accept any additional data, but since I just asked for target.com and you reply with additional target.com thing, it's awesome. So imagine, instead of target.com, imagine it's, facebook.com or wellsfargo.com. So you generate all these requests, you do the reply, you hit the jackpot, you have a collision. Now this remembers, oh, by the way, www.facebook.com is actually at 6666. Next time this victim goes to facebook.com, you will go here, say, oh, I already know where Facebook is, 6666. Suddenly, you connected to this guy instead of connecting to Facebook, okay? Is that clear? Awesome. Of course, this created a lot of panic on the internet, and this gave a big boost to DNSSEC. We will not, go in the details, but the basic idea of DNSSEC is to actually be able to fundamentally sign your DNS information so that you can actually verify using cryptography and not just, very spoofable IDs and other unreliable information where your information is. The problem is that DNSSEC needs big changes in a critical part of the infrastructure. The DNS is something that we rely on a regular basis, and also introduces overhead because you have to sign, encrypt, resign, and so forth. We talked a little bit about DNS amplifications. So this is a problem with open resolvers. These are DNS servers that will respond to queries from anybody. This should not happen. Similar to this are the problem with SMTP, that is open relayers that are used for spam, because then the spam appears to come not from the spamming host but by the server. And okay, so you can ask with any queries all information about domains, and so you can actually do this in order to amplify attack. Of course, DNSSEC make this attack even worse because there is more data, and the attack is very simple. You just send spoofed address, with any queries to this open source domain. Since they appear to come from this IP address, the very large responses are sent to this address, and as a result, it is overwhelming. Another interesting thing with DNS is DNS tunneling. This is something that is interesting because when you connect to certain network, the network will allow you to do DNS requests, but until you pay, for example, or you authenticate yourself, they will not allow you to route IP traffic. So people said, well, what if I'm in control of a DNS server and I'm able to embed data into my DNS requests? Then they will allow the DNS reply, and suddenly I have a tunnel in which I can connect to a network in which they only allow me to do DNS requests, and I can exchange data because my server will receive the DNS request, send it out, send back the reply, and so it will act as a VPN that will bypass, the IP routing restrictions. Okay, and so there are actually tools that can do that using a different techniques that have different levels of stealthiness and this different level of bandwidth. There was a question. Okay. Actually, there were two questions that were asked during the break that I asked to ask in public. What was your question?
Mine was if two different servers have the same IP address as you mentioned, and then how does and they have multiple names, right? So when they have multiple names for the same IP address, then how does the traffic get routed?
So two servers cannot have the same IP address. Okay. A name can be associated with two IP addresses, and two IP addresses can have the same name, but not the same IP addresses. So you can have, for example, you want to do load balance, you decide the name server.ucsb.edu as 128.111.1.1, and 0.3, 0.4, so that when somebody tries to find what this host is, you do round robin between all these IP addresses, so the load is shared among those. Okay, and then you have the case in which you have 128.111.45.70, and this is like a hosting server, and you have www.cats.com, www.dogs.com, And all these domains are associated to this because these are hosted on the same IP. And that's why, for example, in HTTP 1.1, the host header was added. That's, in HTTP 1.0, you just do, you get request, blah, 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 and it's fine. In HTTP.11, you have to do host, semicolon, and a specific domain name, exactly so that you can now distinguish between multiple hosts on the same IP address. Does that answer your question? Good. That was something about worldwide routing.
Yeah.
So, his question, repeat your question.
So if you claim to be somebody else's IP address, what stops information from getting routed to you?
Exactly. So this is hop-by-hop routing. So as we have seen in hop-by-hop routing, you ask to send a packet somewhere, and there are a bunch of gateways that will pass the packet until it reaches its destination. That is right here, right? So what if there is another guy here, and this is A, say, I also have A as an IP address. Why isn't the packet going to him instead? So there is, across the internet, there is a fundamental protocol called the BGP that is used by this gateway to tell to each other, hey, by the way, everything that is 128.111/16 is UCSB and is handled by this guy. So if this guy say, hey, I also have it, people are like, no, that's not yours, which is only partially true because it has happened sometimes that somebody, this is called a prefix. Somebody claimed a prefix, and I don't remember exactly when it happened, but there was some, if I remember correctly, some Eastern European provider that by mistake claimed like a /8 prefix and got the whole internet to send, of course, they blew him out of the water, but they also, for a few minutes, shut down fundamentally correct routing across the internet. That's why this router, they talk BGP with each other. There is a lot of trust in terms of the information. But these are ISP. You cannot go out and talk BGP to anybody, because if you could, then you could do all sorts of shenanigans. Okay, you could advertise a certain thing. And actually, we did, as part of our research, we did an internet-wide port scan of OpenBGP to see, is there anybody who would actually accept, a CNC NAC? And we found none. Okay, so it was one of those negative results. Yes, they thought about it and they don't allow, random connection from wherever you want. Because if they would, these are not, BGP routers, are administered by people that understand networking. And usually they understand, security as well. So we haven't seen a lot of those attacks. We've seen more subtle attacks, which is advertising sort of sub-prefixes of a prefix to, for example, being able to hide traffic. BGP can be very complex, but we haven't seen major BGP attacks so far. That's why.
What would happen if A was able to, gain control of ISP? Right?
Then it will get A's. If this person is able to hack into the IP and push a prefix that say, this is actual B, right? It's not A. And say, hey, by the way, A's address, A's apostrophe IP is mine, then yeah, the next time it will go to them. You'll just suck all their IP and you get all the traffic. But this would be, of course, very noticeable. First of all, A stopped receiving traffic. Probably depending how big is your prefix, a bunch of machines will stop. Usually you don't have prefix with a full IP address. Hey, this single IP address, send it this way. Usually there are prefixes of substantial, usually this subsystems are called AES, autonomous system, and those are the sort of building blocks of the high-level routing on the internet.
But there's nothing like cryptography-wise to ensure that BGP messages aren't tampered with?
No, there is fundamentally these two hosts will talk to each other. They're called peers, and they will only allow connections among each others. So if you're able to do a TCP spoofing and pretend to be this BGP server to this server, you might be able to actually do some damage. But TCP spoofing is now very hard. Awesome. Other questions? Yes?
So about the birthday attack, I don't understand how it's possible to send multiple DNS requests if the victim also caches the request.
It's cached NX domain, which is never cached. Other questions? No, great. That's why you want to do this random domain, so it NX domain when it comes back. Perfect. Let's conclude briefly talking about something that we cannot leave out. The secure socket layer. This is different from the other protocols because it's not per se an application protocol. FTP is the epitome of an application protocol. It just does something. Then you have DNS, which is kind of an infrastructure protocol. It's not really an application. It's not providing, sort of a user service. It's more of an infrastructure. And then we have the secure socket layer, which is instead something that provides encryption end-to-end. And of course, it was developed a long time ago by Netscape to protect HTTP transaction. And there has been the last version, I think it was 3.0, that's been deprecated, and now we talk about transport layer security, which is fundamentally the same thing when it's standardized by the IETF. And I think that this is outdated information. It should be now obviously done. The basic idea of OpenSSL is to provide over socket all the things that a TCP IP connection does not provide, which is authentication and encryption. So integrity and confidentiality and authentication of the communication. And of course, this is done using certificates and the concept of a session. The session is something that is established between two hosts. They exchange, they establish the set of algorithm that they want to use. We saw something similar in the Security Association for IPsec. You have a specific parameter index, and you want to say, I want to use this specific association. In this case, you set up the communication when you connect, and you establish between a client and a server what algorithms they want to use. And of course, this is important because not all algorithms are supposed by everybody. So there is actually a little bit of back and forth, if you want, where one says, hey, I support RSA with this key size, AES, I don't want to use RC4, etc., etc. And the other guys say, well, I also have RSA. That seems the strongest thing that we both have. And I also know how to do AES. That seems like a good idea. And so this will actually lead to an agreement. Fundamentally, each connection there is characterized by random number that are established by the client and the server. The keys they use generate authentication checks and to encrypt traffic, and also sequence number to prevent replay attack. The TLS has two stacks. There is a handshake protocol, which is used to establish the connection, and then there is an actual record protocol that is able to pack and unpack data as necessary. This is the handshake protocol. The client say hello. The server will say, oh, I'm the server. This is my certificate. It might have also, hey, I want to authenticate you as well. Some OpenSSL might require that. most server do not require client-side certificates. And there is the server key exchange, and then the client replies optionally with its own certificate, the client key exchange, and the cipher spec that say, hey, change this, change the encryption to this set of parameters. When this is done, the server say, okay, I agree to that particular set of cipher spec, and from that point on, they can exchange data. So the protocol hello is where you decide which cipher suite you're able to deal and you want to use. Initially, your cipher suite is nothing. So if you want to send stuff in the clear, use TLS null with null null. And then you send a message sending a random number. If you already talked to the server before and you already established a session, you went through the motions of identifying a set of algorithms to encrypt and everything else, and you want to cut it short, say, you remember last time? Let's use that. If that session identifier is valid, you would just switch directly to this. Otherwise, the client specify a bunch of different combination that it supports. It's not just this algorithm and this algorithm, but actually, hey, I can use RSA of this kind using for encryption AES with key of 128-bit and for MD5 SHA-256. Okay, so this is one of the possible cipher suite or combination of things that could be used. Okay, and also a list of compression methods. So the server at that point says, okay, this is my random number. Remember, having two random numbers prevents people from being able to sort of interject into the communication, similar to what's done with WPA. There is a session identifier. If it's the same of the one proposed by the client, we're pretty much done. We don't have to decide much. Otherwise, usually there is a cipher between those that is proposed by the client. And the server says, yeah, I can support that particular type of encryption. This is the key exchange. I don't want to go into the details, but fundamentally, at a certain point, if they decided exactly what are the keys establishing between the two, they can just switch to encryption, and from that point on, everything else is encrypted and everything is secure. The record protocol is very similar to how you would transmit information. You would chunk up the data, would now compress, generate an integrity check for the message, you encrypt everything, and you ship it. So it's nothing specific. The interesting thing is if you want to operate with OpenSSL, you have to familiarize yourself with the tool. The tools, OpenSSL, the actual OpenSSL tool is extremely useful. Allows you, sort of like Netcat, allows you to open connection using socket. OpenSSL allows you, in addition to creating keys, creating self-signed certificates, and all the thing, allows also to actually operate like a socket connection. So it's a sort of like a Swiss Army knife for doing everything SSL. There are also a lot of other tools. S-Tunnel is another useful tool to sort of take something that doesn't have SSL protection and tunneling all the information across the protection. And there are also tools similar to TCP dump that are able to collect SSL traffic. And of course, if you provide the key, you will be able to decrypt the traffic. Yes?
So a tool like OpenSSL, I'm guessing it supports SSL, but
yes.
By default, does it use TLS?
Yeah, I mean, SSL and TLS are fundamentally the same thing. The TLS is the actual correct name for the standard.
Oh, is it the new name or okay?
Yes. Other questions? Awesome. There have been a bunch of attack against TLS and SSL. In 2011, we had the Beast attack. You use a chosen plaintext attack to actually break the crypto. Then there was the Poodle attack. It was a padding oracle on downgraded legacy encryption. It was a man-in-the-middle attack that would allow to sort of choose a lower sort of downgraded protocol. This is one of the downgrade attacks that we named before. If you're able to force people that think they're talking to each other in a secure way to use a less secure way, then you can, for example, you convince them to use RC4, and you are able to break RC4 or similar, and therefore you can actually break the encryption. I would say the most devastating and so advertised that now there is even an XKCD cartoon that described was the Heartbleed attack, which was actually a bug in the implementation and nothing had to do with the protocol. And the basic idea is that it was like this very simple, are you alive, keep alive messages that would be completely random. They would say, hey, they would say, this is the message is 5 characters, send me back this message with 5 characters. So I would say 4, ciao. And you would say ciao back. I say, great. And I say 10,000, ciao. And so it would reply with ciao plus 9,996 more characters chosen randomly from the memory of the web server, okay? Which would contain password, keys, anything. So it was such a simple bug, but so devastating because you could contact any server and suddenly we could get chunks of memory of that server sent to you without any effort. Also, there is another attack, the Freak attack, that was less I would say advertised, but it was another attack against some implementation that could convince to go back to insecure algorithm. Of course, there were also RC4 biases that shows that it was presented at the Using Security Symposium, showed all this sort of problem with RC4 that we also saw in WPA, and fundamentally in 2015 the IETF say, stop using RC4 in TLS. That thing is completely broken. Perfect, right on time. So this concludes this part on application protocols. Of course, this cannot be a complete analysis of what the problems on the internet are. Telnet had tons of problems. Finger, which doesn't exist anymore, fundamentally was used by the worm to spread. So all these application protocols are the fundamental into a remote server, and so analyzing them, analyzing their implementation is a big part of doing vulnerability analysis. And now you fundamentally know what are the building blocks at the network level to be able to influence their behavior, spoofing, hijacking, and similar. With this, I'll stop here, and are there any questions? A moment to read the SKCD cartoon.